So are there any questions from last time? Okay, so this lecture is about contextual bandit exploration. So last time we talked about how to use exploration information. This time is really about talking about how to gather exploration information. And the goal is to sort of kind of gather the exploration information in the most efficient manner possible. Okay, so this is the contextual bandit setting again. And now in order to think about exploration, you need to actually think about what learning means precisely. And the standard answer from learning theory is competition with a reference set of policies. And so you have a set of policies, each of them maps the features to an action, and your goal is to compete with the best of that set. So you want to look at the average over all the time steps of the reward of the policy's chosen action, and you compare that to the average over the time steps of your learning algorithm's reward. As long as you're competing with, then you're doing well. So then the question becomes, how do you create an exploration algorithm which allows you to compete with, so you have a similar reward to the best policy if you had known that in advance? Okay, so.
But you don't know RA.
You are choosing RA. RA is it's the action that your algorithm actually takes. R pi is an action that policy pi takes, or R sub pi of x.
And it's continuously evolving. The policy is learning, so RA would be different for maybe the same state for the same context.
Yeah, so it can depend upon the history in arbitrary ways. So this is a relatively standard little bit of mental gymnastics that learning theory people do, but it's kind of good to understand because it'll come up many other times in your life if you look into these things at all.
Is there any way, I mean, so like the policies, the different classes defined, is it supposed to be all classes or all possible policies, or?
No, it can't be all possible policies, actually, because your regret guarantee becomes vacuous if you try to compete with all possible policies. This is another version of sort of the no free lunch theorem. So the claim is that you must have some bias in order to learn.
Right, so if you learn,
and so if you consider all possible policies, you won't have any bias, and then you won't be able to, there'll be no way in which you can converge to compete. There's too many things to compete with, basically.
Oh, but there's a distinction. I mean, so, but there's no distinction between the policy that you are, between the class of policy that you are learning and the class of policy that exist out there in the world. That's what you mean? No,
I mean, I meant like all possible, like ultimately policy, whatever be the structure, is some mapping from X to A.
Yeah.
Assuming a deterministic mapping, there is, and assuming all space are finite, I mean, there is a particular way which policies can map X to A. If you enumerate all these policies and create like the universal set of all policies, then you're saying that it's meaningless to compete against because you can never.
So let's think about how big the universal set of policies is, right? So if you think back to yesterday or last Monday, we compete. So essentially, what happens when you look at the same complexity bounds, you're comparing log of the number of policies to the number of time steps. And we'll see that later today too. So you need to have it be the case that the log of the number of policies is substantially smaller than the number of time steps, or VC dimension is substantially smaller than the number of time steps.
If it's too long, the bounds are meaningless.
Yeah. So if you try to enumerate all possible policies, so suppose we're just doing binary, and then we have t different time steps. Each of those will have okay. So there's a policy which can choose either action 1 or action 2 at each time step. So we have 2 to the t possible policies.
I'm assuming the vectors are not being repeated.
Well, let's say everything is unique. So every x is unique. So we have 2 to the t possible policies. So log of 2 to the t is t. T divided by t is 1. So it becomes vacuous. So you have to have a number of policies which is substantially smaller than 2 to the t.
So would it be wise to say that the number of policies, the way they are chosen, is that the structure of the policy is fixed and some parameters are being trained around, and the number of policies are determined by the variations in the parameter space?
Yeah. Yeah. So variations in the parameters. So right, exactly. Okay, so now let's think about what exploration is. So there's actually several kinds of exploration you can imagine. But in general, what I mean by exploration is choosing sort of not obviously best actions to gather information so you can perform better in the future. There's several ways to do exploration. So one way is deterministic, another one is randomized. And these differ. I mean, if you think about normal bandits rather than contextual bandits,
John, can you just reduce
yeah,
the volume more?
reduce the volume.
I mean, I don't know.
Say something. Oh no, that's too low volume.
Zero.
Okay, very good.
Yeah.
All right. Okay, so for normal bandits, there are deterministic policies like UCB, right? So what happens there is you maintain the confidence value on the value of confidence bound on the value of each arm, and you choose the arm with the largest upper confidence bound, right? So that's deterministic. You're just choosing given the state of the history, you choose one action deterministically.
Is UCB optimal in multi-arm bandit case?
So there's a little bit of question about what you mean by optimal.
And if I remember, there's a lower regret that you can achieve, and there's some algorithm, I think.
So it is optimal-ish for some notion of optimal.
Okay.
But there's some amount of worst case in that notion of optimal. And so,
I mean, wouldn't we define optimal by the minimum regret? So like, if that achieves the minimum regret, then.
so if you really want to define the minimax optimal,
What is that?
then you need to say something like, so you have a sequence of time steps, and in the last time step, you'll have some information, and there's all possible sets of information that you have. And given those sets of information, you want to compute the lowest regret choice. And then given your choice, the adversary can define things. Okay, let's go to the fully observed setting first. If you're in an online setting and it's fully observed, then you can define a mini-max optimal solution where at the last time step, you are making a decision about what to do, and then the adversary is responding to that in terms of what rewards or losses they give you. And then at the step before that, you can know the value of those outcomes, and you can recompute that minimax, and then you can back that up in a dynamic program to figure out what the optimal action is at the first time step in the sequence. So that's, I can send you a pointer to this later.
Okay, that'll be good.
Now the same kind of thing could be played in the bandit setting, but generally people don't even try, because even doing this is pretty tricky for the fully observed setting, and it becomes substantially more so in the partially observed setting, in the contextual bandit setting. Okay, so that would be optimal in the sense of you cannot come up with an algorithm which is better than this under the assumptions that you're working with. People typically don't try to achieve the best optimal. They try to achieve something which is sort of within some constant factor of the best optimal, because it's much easier to analyze. It's like an amortized analysis of some sort. So amongst the different exploration strategies, for bandits, deterministic, I think, often works pretty well with UCB type algorithms. Randomized can work about as well as, and if you look at some of the best randomized algorithms, their performance is similar to UCB. But the claim is that for us in contextual bandit land, there's several very strong reasons to look at randomized over deterministic. Okay, so first of all, there are no good deterministic algorithms known, and that's kind of a subtle issue. So the reason why there's no good deterministic algorithms known is So because you have a context, it's possible to have correlations across time steps in the decisions that the different policies make. And so if your deterministic algorithm somehow correlated with those decisions, you'd be unable to make an unbiased estimate of the value of a policy. And then it would be very hard to judge which policy is the best one or whether or not you can compete. So the fact that you randomize allows you to break all those correlations across time steps. It makes everything its own little experiment, basically.
I mean, I thought like when you present the states in the contextual bandit setting, those states are independent. Those context vectors are independent IID samples from the unknown distribution. Is that so? There's no correlation.
So there's two variations of the contextual bandit setting. One of them is things where things are IID from round to round. I think that's easiest to think about, but it's actually even an adversarial version. Regardless, though, the problem is not in the IID-ness of the context. Those can be independent. The problem is in the correlation of your valuations of the policy. So if you had a deterministic algorithm, which used the history in some deterministic way to decide what to do, then it might be the case that you end up overvaluing a policy because it's hard to understand how, but it's hard to rule out. So you want to rule out the possibility that your estimator for the value of a policy is biased. And we don't really know how to do that with a deterministic contextual bandit algorithm.
I mean, I'm just not clear. I mean, where this bias is coming from, but maybe I think we can take it offline.
Okay, so let me tell you a couple counterexamples for contextual bandits, and maybe we can think about what those imply as far as what are good algorithms. Okay, so let's think about a setting where action 0 has reward 0 and action 1 has reward 1, and our policies all play action 1, except sometimes they defect and play action 0. Okay, so when we're randomizing, we don't want to play the action 0 very often, because that would result in a poor reward. And in fact, when we get to the more advanced algorithms, we'll discover that the probability that they place on action 0 is like 1 over square root of t, where t is the number of time steps. So that the sum of the regrets is like root t. But what you could do is you could ask, as an alternative, you could say, suppose I have no probabilistic estimator. All I have is, what is the performance of the policy so far, or something like that. And then I could say, oh, I want to choose I want to figure out which actions are chosen by some policy that's good. And since one policy on each round will defect and choose the reward 0 action, that would mean that you randomize 50-50 between the 0 and the 1 actions, between the two different actions. And that would mean that the regret that you would suffer is like t over 2. Okay, so what does it say? It says that you can't look at the set of actions which a good policy chooses and decide what to randomize based upon the actions that projects to. You actually need to form a distribution over policies rather than distribution over actions. And then when you have distribution over policies, where all the policies are good, you'll be able to guarantee a small regret. I feel like we're getting to the end of the lecture. Maybe we should. Okay, so let's get to the end of the lecture, and then we'll discuss this in more detail. Okay.
Question.
Yeah.
So when we say deterministic, does this mean determined based on all the history, all
Yeah.
the past conflict? Okay.
Yeah. Okay, so another reason to do randomized is because of last lecture, where we said, look, we can actually support off-policy evaluation effectively, right? So the way that we were estimating the value of policies relied on randomness. So if we wanted to do something deterministic, we'd have to define some alternative to that. And then the last thing I think is actually fairly important in practice. When you have a deterministic policy, and it takes some time for the feedback to actually occur, your deterministic policy is going to be kind of stuck doing the same thing over and over and over again. So it's going to gather the same information over and over again about the quality of its policy. And then if you look at what happens to the regret bound, you end up kind of multiplying the regret by the delay factor. Well, if you have a randomized algorithm, you end up adding the delay factor to your regret.
But if your policy is relatively good during this time, you will get reasonable behavior.
Yeah, but we're trying to do exploration, so we're trying to improve the value of the policy. So I think we're typically assuming that we don't have a good handle on the policy, and then we're trying to narrow in on what the best one is. And the goal is to narrow in as quickly as possible. So when I say randomize, I don't mean pointless randomization.
Yeah, you mean like.
I mean randomization for the purpose of gathering good information. Okay, so this is the simplest possible exploration algorithm. It's explore tile, then follow the leader. So initially, you have no history. For the first tile rounds, you observe your features, you choose your action uniform random, and then you observe your reward, and then you add this quad to your set of your history. Okay, and then after the first tile rounds, you just use the empirical best policy. So if you think about it, this is kind of what happens with a clinical trial. I mean, you do a clinical trial, you see what's the best, and then you go with it. And it's just deployed to the population at large and used forever after.
So what is empirical best?
So we have that estimator that we talked about last time.
Mm-hmm.
We can use that estimator to value the policies. We can choose whichever one of those policies is the empirical best.
Okay.
So does everyone remember the reward times indicator function of pi of x equals a, all that divided by p from last time? Yeah.
So in this case, all the propensities are equal, so we don't really have to worry about it.
Yeah, it's kind of a no-op here.
Yeah.
Okay,
But
so
after the T minus tau steps, we still keep updating using that.
no, there's no more updates after that because you no longer explore after the first t minus tau steps.
Oh, then it's all deterministic, right?
Yeah, and there's no more updates because you don't have any new information basically.
So where are the updates here? I mean,
What's that?
Where are the updates here?
There are no updates until around tau, and then you do all the updates at once.
Okay. Okay. So it's like, okay, so you put it in the comma. After that.
Yeah. Okay, so what can you prove about this? Well, you can prove for any distribution in any set of policies, you have a regret, which is like, this is an average regret, which is like tau over t plus the square root of number of actions times log number of policies, all that divided by tau.
This is a regret after T minus tau, like after the tau rounds, right?
It's the regret for the entire t rounds.
Oh.
Okay, and you can probably see how the proof for this works because it's very straightforward. You just say, look, after the tau rounds, you have tau piece of information, and you use one of these standard large deviation bounds, which gives you the value of the policy minus the expected. Oops, I forgot missing a parent. Minus the expected reward of the policy is bounded by this square root term, right? And here you can see we have the log of the number of policies compared to the tau, the number of time steps. Okay, so that says that.
Like probability 1 minus delta.
Yes. Yeah. So high probability here is 1 minus delta. I should write that more explicitly. All right, so then you're going to suffer this kind of instantaneous regret for t minus tau rounds. So it's t minus tau over tau, and then you have no control over the first tau over tau round. So it's tau over t, so and then you add it together and you get the answer. Okay, so then the question is, if you optimize your choice of tau, what does the bound look like? Any guesses?
Somebody can take the derivative, set it to 0.
Take the derivative, set to 0. Yeah, so it's kind of good to see this form because you'll see bounds where you have this 1/3 or 2/3 power, depending on how you represent it, fairly often. So if you take the derivative, set to 0, and so forth, you end up getting something like an A log number of policies over tau to the 1/3 power. So if you contrast this with the Hufting or turnoff bounds in supervised learning, there you have a 1/2 power, and you have no dependence on the number of actions. Right? So the 1/3 is worse than the 1/2, and the dependence on the number of actions is worse than no dependence. Okay, so the tau plus 1 over square root of tau, optimized for tau, gives you that 1/3 power.
Here, are we assuming that the policy is somewhat tabular? Like there is
There's a new Zoom link. Check your email.
No form is.
just like some kind of a table.
There's no assumption about the structure of the policy. The policies set can be arbitrary. Okay, so this is the easiest approach. And I think it's often the case when people are first starting to do exploration in practice. They're just like, I'm just going to explore a bunch and then I'll get a data set and then I'll work with it. So it's kind of doing an explore tile-like approach. The disadvantage I see is it doesn't adapt. So if the world changes, if it's non-stationary in some way, you don't cope with it at all. You also have both under-exploration and over-exploration. So you under-explore because you don't get any, often T is something which actually grows with time. That's why we call it T. And that means that for any amount tau of initial exploration that you do, you will eventually become too little if you're trying to minimize regret.
Can't you just keep on doing it? Like after every few steps, just use that entire situation.
We'll get to that in a minute. The other issue is that you also do over-exploration. So it may be that there are some really bad choices, and you just keep exploring them throughout that first initial tau time steps. Okay, so can we do better? And the answer is yes. So we can do epsilon greedy, which is along the lines of what you're suggesting. So with probability 1 minus epsilon, you're going to act greedily. And then with probability epsilon, you're going to act uniform random over the other actions. So the P is either 1 minus epsilon or it's epsilon divided by magnitude of A minus 1. So the number of actions minus 1.
So when you say in learn, you're going to update after every tuple?
Yeah. So I think we have a cycle. Can somebody shut off their speaker?
Yeah, escape.
Just lower the volume. It's not mystery.
One question.
Yeah.
If we do epsilon greedy style algorithm, is it easy to choose adaptive epsilon over time?
All right.
Philip, can you help him?
I mean,
I think it's some weird problem.
You cannot hear me, correct?
I hear you. There's just a lot of echo going back and forth. It'd be good to get rid of the feedback.
So in epsilon greedy style algorithm, could we easily choose epsilon adaptively over time?
Yeah, so that's a good question. There's a paper.
Does work now better?
Yes, it sounds much better. Good. Okay, yes, you can choose epsilon adaptively over time. That requires a little bit more effort. I'll mention a little bit more about that in a moment.
Got it.
Okay, so for epsilon greedy, you have a regret, which is like epsilon plus this square root form. And so you can see again that we have an epsilon plus a 1 over square root of epsilon type thing. And when you optimize that, you end up with a 1/3 power again.
I have a few questions.
Yeah.
What is A, big A?
Big A is the set of actions.
Oh, okay, I see. Oh, so that's size, not.
Yeah, so it's the size of the set of actions.
Absolute value. And then when you say choose uniform random with other A, does that mean everything except for the optimal
Yeah.
A?
So there's sort of, I could write this down in two ways. I could say with probably epsilon you choose at random A, or I could say with probably epsilon you choose a random other A.
so when you say choose learned A in the first option,
Yeah.
and then you observe, and so with the probability of 1 minus epsilon, then you observe, you learn with probability of 1 minus epsilon the tuple. Shouldn't you have, if you're sampling for your policy, shouldn't you have the probability that it's sampling policy, or just because the sample is sampling?
Should you have what?
So you don't want to include the probability of A according to your policy here in the tuple, where you include 1 minus epsilon.
Probability of A according to your policy. Okay, so let me back up to what I was saying before. There's two different ways you can write down epsilon greedy.
Mhm.
One involves, in the epsilon case, randomizing over other actions.
Mhm.
And one involves, in the epsilon case, randomizing over all actions. Okay, so if you randomize over all actions, then the probability is a little bit more complex to write down, because the probability of the greedy action is at 1 minus epsilon plus epsilon over the number of actions. Because there's two ways to choose.
I think your question
The
is
learning is deterministic.
yeah, the learned A is a deterministic of the policy, assuming there is no tie breaking.
So you're not.
Learned days are not deterministic because with probability 1 minus epsilon you play them.
Oh yeah. But I mean it's not sampled. Like A is not
You don't
sampled.
sample from your policy. You take the Argmax policy, for example.
With probability 1 minus epsilon.
Yeah. But, assuming you're in that branch,
Yeah.
the first branch,
Yeah.
you're deterministic.
Yes.
Okay.
So you could choose to treat that as deterministic and ignore those events, or you can choose to treat it as randomized and learn from those events. Here we're choosing to treat it as randomized because randomized captures more information than deterministic.
So if it is randomized,
Go ahead.
if it's randomized, then choosing learned A is a probabilistic thing. And wouldn't we note like 1 minus epsilon times probability of choosing whatever you chose from your learned policy?
So P of A.
So I think what you're saying is if the policy is randomized,
Yeah.
then you would like to express that in your distribution over actions. That's right. So I'm thinking about the policy here as being deterministic.
Okay.
Mhm.
That's answer.
So I was trying to answer your question about the epsilon greedy.
Mhm.
So you understand what I'm saying about if you phrase epsilon greedy the other way, then the probabilities become a little bit trickier because you need to account for the two different ways to choose an individual action. One from the 1 minus epsilon case and one from the epsilon case.
So other with respect to not the one that is chosen by the deterministic policy.
Yeah. And internally in VW, we actually do it the other way, so that you can make epsilon be 1 rather than half or whatever. Details. Adith had another.
So the analysis here is it like the same as the follow the leader, because it seems like epsilon is just tau by t.
Yeah. I mean,
it's just like the order doesn't matter, and you just.
We're in the ID setting here. So we're imagining there's a distribution over X and a hidden R vector. And so follow the leader is equivalent to empirical risk minimization.
Yes.
And then you're just trying to work out how big the deviation bounds are, which is what gives you this.
But the difference I see is, like, since we are also recording the action chosen using the learn policy or learn A,
Yeah.
we also include that in our history and probably learn using that also, right? In follow the leader, we didn't even include the after the tau step, we didn't learn anything.
When you say follow the leader, you're talking about the explore tau. All right, explore tau rather than follow the leader. Yeah.
Yeah, then follow. Yeah, this one.
Yeah.
So here we don't learn from the after the tau steps, right?
That's right.
And in the other one, we learn at every step.
Yes.
Epsilon.
Yes.
But our they couldn't, even up to this, our they couldn't.
Well, they give you the same functional regret. Yeah. But they are different too. Right. I don't know how to answer that. They're obviously equivalent in terms of the form of the optimized regret when you optimize the parameter as well. But they actually differ in the constants. And the epsilon greedy has a strength which the tau first does not, right?
Yeah.
So in particular, it deals with adapting problems where tau first is not.
John, just a minor digression.
Yeah.
So how does these things work when action space is continuous? So then what would your modulus A would be?
Yeah, so continuous action space. So continuity alone is not a strong enough assumption to make exploration tractable. So you need to have something like a Lipschitz condition or some bounds on the derivatives or things like that to hope to have enough structure.
So my question, I mean, I don't want to go in, I mean, I don't think probably we'll have time, but I mean, these bounds will no longer hold, right? Because yeah.
So yes, but if you have a Lipschitz condition, then you can start thinking about how many truly different actions do you have. I agree. It'll be different bound, but
that's
you can start thinking about what happens when you have. I mean, if you have a Lipschitz condition on the value of different actions.
But when you say Lipschitz condition, you mean FU minus FU equals to U minus U minus U.
Yes. So you want some bound on how much things with two actions which are this far apart have at most some constant times that distance apart, difference in their rewards. Then you can start thinking about.
So you need Lipschitz continuity on the reward function.
Yeah, that would be typical. Okay, so epsilon greedy is, I think, a little bit more difficult to use because you need an online learning algorithm. You have to be updating constantly. It does adapt when the world changes. That's good. You still tend to overexplore, and in particular, if you have a fixed epsilon, you kind of are guaranteed to overexplore as time goes on because you want your epsilon to be decreasing with time. There's also a paper on epic greedy exploration, which I did a long time ago, talking about having an adaptive version of epsilon greedy. It doesn't give you any difference in analysis for optimized epsilon, but yeah. So what is the right epsilon? The right epsilon. So if you have a set of plausibly good predictors, you want your epsilon to be set to sort of the difference in losses of those possibly good predictors. Does that make sense?
Yeah.
So at some time step t, you've narrowed down to things which are within some epsilon of the best, and the epsilon that you want to explore with is that epsilon. Okay, so now the question is, can you do even better? And the answer is yes, of course. So I'm going to tell you two approaches which are better. One of them is kind of empirically better. The other one is kind of theoretically better, and maybe sometimes empirically better too. So there's an approach called Thompson sampling, where if you're a Bayesian, you say, oh, I have a posterior, and I'm going to draw from the posterior and act according to that draw from the posterior. So that's kind of a heuristic. There's no real guarantee associated with that. There are some bounds people have worked out. They tend to have weaker quantification than for the best algorithms that we know about. But nevertheless, empirically, this does work fairly well in many cases. Now, one problem with the Thompson sampling approach is that it's very Bayesian, which typically means intractable in practice. So, so in particular, calculating posteriors can be very intractable. So how do you get around that? Well, you essentially do a bootstrap. When I say bootstrap, does everybody know what I'm talking about? Or nobody? Who knows? Okay, you don't know what a bootstrap is. Okay, excellent. All right, so I'll show you in a moment. There's a way to manipulate a data set so as to kind of get an approximate posterior. And then, okay, so let me just tell you the algorithm, and then we'll talk about why we're doing certain things. So repeatedly, you observe the features. We're going to have a set of policies that we're maintaining, and we're going to just draw uniformly from that set of policies in order to create a distribution over actions. So we're projecting distribution over policies with a context into distribution over actions. And then we draw from that distribution over actions, and then we observe a reward, and now we're going to update each policy some number of times, which is random, with the event that we observed.
What is this BR pi x equals to A?
Wait, what?
So the probability that pi of x equals A, we have a set of policies,
Okay.
and the question is, if we draw a random policy, uniform random policy from our set of policies, what is the probability that that uniformly and randomly drawn policy chooses action A?
So this set of policies is not all the policies under your model. You actually maintain like a.
We're maintaining an explicit set of policies.
So that's why it's called tagging. So basically,
Yes.
like a bunch of hot stamps, but yeah.
Yeah.
Again, some.
So you can approximate Thompson sampling with a bootstrap, which is okay. So typically, this is stated in a batch setting. So you sample with replacement from your set of samples. So you have n samples, you sample n times with replacement. So about a 1 minus 1 over e fraction is sampled at least once. Yes, that's right. And a 1 over e fraction is sampled 0 times. And then some things are sampled twice, some things are sampled 3 times, sometimes sampled 4 times. It falls off exponentially, so typically nothing is sampled more than log n times. Okay, so this is a well-known way to create a diverse set of predictors. You can do this bootstrap sample many times, and then you could do some sort of majority vote or whatever, and that would be called bagging.
So you don't want to maintain some kind of probability of using this policy conditions on the state. I mean, you're not doing it here. It would be interesting.
We don't want to maintain what?
So right now you're choosing PA given X without really explicitly modeling the probability of the policy being valid for this state. Something you can think of. So
what does valid mean?
it's good for this state. So one policy is good for this room, another policy is good for that room, and you have some kind of problem.
Yeah. So we're not doing that. So we're just saying, well, I mean, we're updating the policies. So we're imagining if there's some big policy set, and our learning algorithm is kind of greedily searching through that big policy set for the good one. The best predictor in that policy set with respect to this update process will be the same as the best predictor with respect to the base problem. But there will be some variance which is induced by the differing updates according to that Persona 1. So the Persona 1 is a way to approximate the sampling with replacement in an online setting. And it's essentially identical.
Very loosely speaking, it's some kind of regularization to it.
So you have a set of I's, right? I mean, that's why it's lagging.
Yeah.
So when you take the step number 2 with respect to which I?
So step 2 is with respect to a random pi.
Oh, so
Or rather, steps 2 and 3 are effectively with respect to a random pi.
Okay, so random pi is chosen.
Yeah. So let me back up now. If you just act according to random pi, you can do that. But you'll end up losing because you'll have more variance than necessary. Your probability will essentially always be 1 over the number of policies. And that means that your estimators will be kind of off. So that has too much variance. You really want to coalesce the probability of an action, coalesce down to the probability of an action. Because the probability of an action, I mean, maybe every single policy chooses the same action, in which case the probability of that action is 1. So the ability to describe that is important as far as the variance of your value estimators for policies.
So in 2, you're marginalizing overall your set to randomly sample it.
I would say projecting myself, because you have a distribution on policies that you're projecting to a distribution on actions using the features.
So given your features and you have some policies and you have a probability distribution of the policies, then you say the probability of the actions is like each policy says, this is my action. And so then you instead have like that. Yeah.
So you're looking for the fraction of the policies which choose that action.
Yeah.
So what's the probability of a policy? This is something
So,
determined?
yeah, it's just uniform over the set of policies you maintain.
Wouldn't it make more sense to use a Bayesian prior based on some kind of performance statistics? More for practical.
I don't think it would actually make a difference in practice because all of these policies are being updated by the same process. So they all kind of have the same expected value.
They're like little and then just reduce the variance.
So if you,
I don't know.
if it's uniform, you're basically voting.
Yeah. Yeah. So you're voting on actions and the distribution is proportional to the number of votes. So this is a pretty good policy in practice. So it avoids unnecessary exploration. So if there are really stupid things that all policies agree are stupid, then you just don't explore that anymore. It's known to work well empirically. It's a little bit heuristic in the sense that the theoretical guarantees that go with it are weaker than the standard theoretical guarantees. But there are some guarantees. So what you can typically prove is that if the problem, so let's go back to the full Bayesian setting. In the full Bayesian setting, if the problem is drawn from the prior, then in expectation over that prior, you can prove something about the performance of this kind of algorithm. So in particular, the way that this worries me is often we're working with misspecified priors or misspecified policy sets. And so it's a little bit weaker, but it can give you good performance. And then the other thing that I would emphasize is that it kind of empirically it can underexplore. So how do you see this? So the way you see this is, suppose you have a prior which is uniform on a set of policies, and every policy chooses action 1 except for one policy chooses action 2. Then the probability of choosing action 2 will be very small. It'll be super tiny. And that, because you never choose action 2, you don't have a good estimate of its performance. Your estimate of the performance of action 1 gets updated, and all the policies choosing action 1 get updated, but not for the policy choosing action 2. And so the same problem can repeat over and over and over again. And so you just fail to compete with that one policy which chooses action 2. Okay, so let me tell you instead a theoretically sound algorithm which addresses that problem, and then we can debate how well it works empirically. I don't have a good sense yet, but I know a little bit. Okay, so we're thinking about a general structure for algorithms, which is, you know, for each iteration, you see some context, you choose an action, and then the world is going to react to that. And then the things you need to fill in are what is the distribution QT that we draw a policy from, and then how do we handle the update of that distribution? Okay, so question is, what is a good distribution to be drawing from? So now we're getting to the counterexample that I was telling you. So you could imagine choosing a QT, which is just uniform over actions, or uniform over the actions which good policies choose, and that would not work, right? You could imagine choosing a QT which is uniform over all policies, and that would not work according to the example that I just told you, right? So you have this explore-exploit trade-off in how you want to define the QT. So you want it to have a small weight on bad policies, but you want it to kind of support the set of good policies. So you want it to be to capture the set of actions that a good policy takes to a large extent. Okay, so let's define a few things. We have this way of valuing a policy that we talked about last time. We have an empirical regret, which is the difference between the best policy's value and this policy's value. We're going to have some minimum probability of exploration, which decays like 1 over t, or 1 over root t, sorry. We're going to have kind of a measure of our regret certainty, which is the b sub I. That's a little bit harder to understand, but okay. Okay, so we're going to find a distribution Q over policies pi, which satisfy 2 constraints. We want the estimated empirical regret to be small, and we want the estimated variance to be small for good policies. And what that looks like in terms of a formula is something like this. So the first one is estimated regret. So to look at the estimated regret, you need to think about the expectation with respect to Q of this B pi. And then for the estimated variance, you have, for all policies, 1 over the probability of the policy's chosen action. And there's this little notation mu that means that we kind of impose a minimum probability on the action according to whatever mu is. Okay, so this is, I think, a little bit much to absorb quickly.
What does empirical regret mean?
So empirical regret, so you have an estimator for the value of pi, an estimator for the value of pi prime. And the empirical regret is just the difference between
let's say
these.
like you evaluate another policy using the history of the
Yeah. Okay, so we have a way of forming a Q which optimizes this explore-exploit trade-off. It tries to minimize our empirical regret while also providing enough support on the good policies to have a small Okay, so now the question is, okay, so this is what we want. We want to satisfy these constraints. And then the question is, how do we do that? When the answer is, well, we're going to use another form of reduction. So we're going to reduce to an Argmax Oracle. So let's suppose that instead of only knowing the reward of the action that we take, instead we know the reward of every action. Right? So we have this, so it'd be the cost-sensitive classification setting. Let's suppose that there's some oracle we can give, and it will tell us the best policy in a set of policies according to the values that we feed into it. Okay, so we're reducing to cost-sensitive classification, and the only difference between this and what we saw last lecture is that it's important that the set of policies be not all policies, because otherwise exploration wouldn't make sense. Okay, so then we cook up, an estimated value here, which is the value of an action that we talked about last time when we talked about how to reduce, plus this thing here, which, okay, so the important thing is it has 1 over the probability of that action. So what that means is that we're going to sort of seek to avoid actions that we have chosen previously. Right, so suppose we've partially formed a distribution Q. Then for actions that are chosen by the distribution Q so far, then the Q will be large, so 1 over Q will be relatively small. And so we'll end up preferring the actions where the Q on that action is small. So this is a way to induce diversity over actions. So the fundamental thing is we must get a support over the set of good policies.
There's something like UCB. Maybe not. I mean, it's just like it has an additional term which reduces as you take more and more actions.
It does reduce as you get more and more actions, but the fundamental thing is we're trying to cover the good set. So you have a set of good policies, and then we want to, when we're doing the Poisson of 1 type covering, we're just kind of randomly hoping that a random cover will cover things. Here we're trying to explicitly construct a cover, essentially. We're saying, I want you to choose a policy which gives good value, but which avoids the actions that are previously taken. Okay, so then the mixture of the policies that we get out of this Argmax Oracle will form that Q. Okay, so this is a little bit non-trivial to prove. It's a fair amount of fun. You can prove that the regret is like a square root of the number of actions times log number of policies divided by t. So compared to the previous epsilon greedy type things, we went from a third power to a square root power. So that's a win. But we still have it depends on the number of actions. You can try to minimize the number of calls to the cost-sensitive classification oracle. It ends up being the case that you need like a square root of t calls. You can get a lower bound on how many calls are needed. It's also like square root of t. You can get a running time. It's like t to the 1.5, so not quite linear. And this is a paper that we had at ICML in 2014. So this is relatively recent stuff. Okay, so are there questions about the structure of the algorithm? I think the exact details, you really have to read the paper in order to, or you can spend a lot more time. But the structure of the algorithm should be reasonably clear. Let's go back. We're going to be acting according to this policy drawn from this QT. And we're going to form these QTs by having policies which, or we're going to form them by reduction. We're going to learn a set of cost-sensitive classifiers. We're going to use the estimator for the value of a policy that we talked about last time, just a double robust or even just an IPS type estimator for the value of each action. But then we're going to add a term which causes the policies to try to avoid each other. So they try to predict differently from the other policies, which are also good. So we try to find a covering set which has good performance but also predicts differently. All right, so let's see if we can have a little bit of time. Let's go here. Right, so we have this RCB1 data set again. It's the label is now 1 or 2 because we're treating it as a multi-class. And we can now play with different exploration algorithms. That one's slow. Let's try. Oh, okay, so let's say we explore for the first 20,000 examples. And then what you see is for the first approximately 20,000 examples, the performance keeps getting better and better and better. And then it kind of saturates, and there's no improvement in the performance as we go. All right, so we get 0.077. And then you can also do epsilon greedy. And so for epsilon greedy, the improvement is slower because our exploration data is not quite as good at the beginning, but it keeps improving. And so I'm telling you some relatively tuned parameters, empirically tuned parameters. So what you'll end up seeing with epsilon greedy is that it actually doesn't quite improve to be better than the epsilon, the tau first like approach. Okay, so why is that? Well, why is it the epsilon greedy does not compete with tau first? Here we're at 12.7%. What's that?
Over exploration.
So I've kind of, so you can pull this down and you can play with it yourself, but I've kind of tuned the epsilon here to be reasonably near to optimal. So I think the degree to which we're over exploring is about the same as for tau first.
But isn't it like the steps we are like towards the end, we should just be sure about our policy and like that 0.1% is cognitive error?
Yeah, yeah, that's right. So it has to do with the question about adaptive epsilon. Here we have a fixed epsilon. And what you would prefer is at least to have the epsilon shrinking over time. And then really, in some sense, what you would prefer is that all the exploration happened at the beginning, which is exactly what the tau first does. Because if it all happens at the beginning, then you can leverage that for all the rest of the samples. But if it's happening throughout the process, particularly uniformly throughout the process, as we're doing here, then for half of, typically, so our random exploration half the time will be in the future with respect to the example that you're judging now. So you're sort of losing half your exploration data by using the epsilon greedy approach.
Surprisingly, does it show up in the feedback?
It does actually. You get a factor of 2 in the regret bound.
Oh, the constant.
But it's just in the big O. Okay, and then you can also do bags. So what I would run with is, oops. So this will take a while. So maybe we shouldn't do this one first.
But is it already running like 16 policies?
So there's 16 different policies, each trained with this Poisson 1 sampling process. And you can see that the performance is getting better and better, but it's substantially slower because there's 16 policies.
What are these policies again?
What's that?
What's the structure of the policy?
So each policy uses a reduction to custom classification. So, and then each custom classifier is getting reduced to just plain old regression. one different regressor for each action.
Is it like linear regression or?
It's just linear right here. Okay, so that will take a while. I don't. Well, let's come back to that one. And then you can also use this cover approach. It turns out that you really only need a combination of one policy and a decaying learning rate, which is pretty near to Epsilon greedy with an adaptive form. Gives you a very good performance in this data set. And it's good computationally as well as statistically.
Is this code on GitHub?
Yeah. So the code is on GitHub. Maybe so I believe that the data set is also on. I'll put the data set into the directory on hunch.net, so you guys can play with it if you want.
Okay.
Let me. Oops. There. Let that one run in the background. Okay, so the performance here is for bags is almost as good as cover, but still a little bit worse. Yeah, oh well. All right, so I probably need to update this. Yeah, so I think the thing to look at from this is the relative times. So if you just do supervised learning in the same kind of reduction structure, it's about 5.3 seconds, and you get the best performance. If you do online cover, it's slightly worse, but you're handling the whole exploration trade-off well, and it's only like a factor of 2 or 3 worse computationally. If you do bagging, it's much worse computationally, but still pretty good statistically. If you do tau first, then it's actually very good computationally, but somewhat worse statistically. And then if you do epsilon greedy, it's pretty reasonable computationally, but a good bit worse statistically.
Why is a linear UCB?
Yeah, so because we're boiling down to a linear predictor, you could try to do lin UCB. So lin UCB is an algorithm for handling contextual bandits in the linear case, when you're assuming that the world behaves in linear fashion. Now, it ends up working pretty poorly. And the reason why is because this data set has a lot of features. So it has 60,000 or so unique features, more when you do the n-grams and the skips. If you try to, so lin UCB involves the matrix inversion in an online fashion, which you end up wanting to approximate, and it ends up taking an enormous amount of time and not working very well. Yeah?
Why is the epsilon greedy performance so much worse than the initial DAO thing? I think we concluded they were similar.
Yeah, so they're similar functionally. So the curves, I think, as a function of t would look about the same. It's just that they'd be offset from each other. And when you do the analysis, you see that epsilon greedy is actually a factor of 2 worse than like a tau first approach. And the fundamental reason for that is that if you think about picking a random exploration and a random event that you want to score, with probability of half, the exploration happens after the scoring. So you cannot use it to inform the policy. So with tau first, all the exploration happens first, which means all the most informative events are being leveraged to make good predictions in the future. But with epsilon greedy, that's just not true. A lot of exploration happens after the event that you're scoring. So that I think is a fundamental reason why epsilon greedy is not quite as good as tau first. Okay, so there's some references here. I'll put links to them up onto the website. Are there any other questions right now? Okay. All right. See you guys next week.
Thank you.
I guess I think we'll